So now we look at high pass filters. So you're going to see that a lot of the math is generally the same, but we're just now going to look at a filter that passes the high frequencies and kills the low frequencies. So the figure shows a block diagram again and a general response curve for a high pass filter. The frequency considered to be the lower end of the pass band is called the critical frequency. Just as in the low pass filter, it is the frequency at which the output is 70.7% of the maximum. Okay, so that's your general description of what we're going to be looking at here. So we'll look at some of the math now associated. A basic RC high pass filter then is shown. Now you can see that we have the output taken across the resistor instead of the capacitor. When the input frequency is at a critical value, again X sub C is equal to R, and the output voltage is 0.707 times the input voltage, just as in the case with the low pass filter. As the input frequency increases above the critical frequency, X sub C decreases, and as a result the output voltage increases and approaches a value equal to the input voltage. The expression for the critical frequency of the high pass filter is the same as that of the low pass filter. So we start with the same mathematical relationship here, 1 over 2 pi RC. Below the critical frequency, the output voltage decreases or rolls off again at a rate of minus 20 dB per decade. So if we look at the Bode plot below, we can see that representative. Okay, so we see the ideal in red, the actual plot in blue. So for this example, we're going to make a Bode plot for that circuit that we have presented here, 0.047 microfarads and a 330 ohm resistor. So if we insert those values into the relationship 1 over 2 pi RC, then we get 10.3 kHz, or approximately 10 kHz. To the right then we see the idealized Bode plot, again with the Bode plot in red, the actual in blue. Okay, again plotted on semi-log graph paper. The approximate actual response curve then is shown below the red one. Notice first that the horizontal scale is logarithmic, the vertical scale again is linear. The frequency is on log scale and the filter output in decibels is in linear scale. So make sure you get this straight in your head. The output again is flat, this time above F sub C, approximately 10 kHz. As the frequency is reduced below the critical frequency, the output drops at a negative 20 dB per decade. Thus, for the ideal curve, every time the frequency is reduced by 10, the output is reduced by 20 dB. A slight variation then occurs between the actual and what is plotted for the Bode plot. For the RL high pass filter, again we have switched the components. Now we're going to take the output across the inductor. Again, we're looking at that same relationship where the critical value X sub L is equal to R and the output voltage is at 0.707 times the input. As the frequency increases above the critical frequency, X sub L increases, and as a result the output voltage increases until it reaches the input voltage. The expression then for the critical frequency for the high pass filter is the same as the low pass filter. Again, we look at the phase shift in a high pass filter. Both RC and RL high pass filters act as now lead circuits. Recall from chapters 15 and 16 that the phase shift from the input to the output for the RC lead circuit is the inverse tangent of X sub C over R, and for the RL lead circuit, inverse tangent of R over X sub L. At the critical frequency, X sub L is equal to R, and therefore phi is equal to 45 degrees. As the frequencies increase, phi decreases towards zero as shown. So again, this looks similar to the previous one we saw, but now we're above in the positive angles instead of the negative angles. So in this example, we're going to look at the phase shift in a high-pass filter. Find the value of the capacitor so that X sub C is approximately 10 times less than that of R at an input frequency of 10k hertz. In B, if a 5-volt sine wave with a DC level of 10 volts is applied, what are the output voltage magnitudes and the phase shift? So there's our circuit, simple RC circuit. For part A, determine the value of C as follows. So we know that X sub C is equal to R, but in this case we want 1/10 of the value. So if we take 1/10 of 680 ohms, we get 68 ohms. Now we use our reactive formula. In this case we're going to solve for C. So we swap X sub C and C from the numerator to the denominator on both sides, and we get 0.234 microfarads for the actual capacitance value. Using the nearest standard value of the capacitor, 0.22 microfarads, then we can solve for X sub C. So in this case, we go back to X sub C is equal to 1 over 2 pi FC, and we get 22 ohms. So you notice here, and this is something that you will see and will recur in solving problems, is you're going to have to look up sometimes and find out what's the closest value that a manufacturer actually makes of a capacitor. They don't make a 0.234 microfarad. There might be some tolerance that will get you close to that, but you need to find the closest standard manufactured capacitor to use. Otherwise, you'd never be able to design this circuit and insert that capacitor. In the second part, determine the magnitude then of the sinusoid using the voltage divider formula. So now we go back to that formula that we've looked at several times now. In this case, we're going to put our values in for R and X sub C, and when we do, we get an output voltage of 4.97, approximately 5 volts. The phase shift then is the phi, the inverse tangent of X sub C over R, gives us a value of 6.04 degrees. So not a very big angle. So at the frequency of 10k hertz, which is a decade above the critical frequency, the sinusoidal output is almost equal to the input magnitude, and the phase shift is very small. The 10 volt DC level then has filtered out and does not appear at the output. So when we come back, we'll take a look at the series resonant bandpass filter.